Welcome to chapter 16 when we talk about additional aqueous ionic equilibria. So this is really just a continuation of chapter 15, but focusing not just on dissociation of acids with water or dissociations of bases with water, but what happens when we have an acid and its conjugate base or a base with its conjugate acid. And in this case, really talking about buffers. We're also going to talk about how to stress out buffers when we know what buffers are. And then we're going to get to titrations. So what happens when we take a weak acid, we titrate it with a strong base? What happens with a weak acid and weak base? We're going to do all sorts of different derivations of titrations, which is really what a neutralization reaction is. But more on that next week. So when we first start, we're going to go through the chapter 14, the chapter 16 objectives. So really, we're going to talk about the buffers and what a buffer is and how it uses what's called the common ion effect, which is really just an example of Le Chatelier's principle that we've already learned in equilibrium chapter. We'll then talk about pH buffering, how to prepare a buffer to a specific pH, and the buffer's ability to resist changes in pH when we add strong acids or add strong bases. So this is focused on the first three sections of our chapter 16 reading. The first section really focuses on applications of buffers and specifically, I think, ocean chemistry. So you can really just get to chapter 16.2 and chapter 16.3. And then our titrations that we'll be focusing on next week is all going to be 16.4. We'll get to that later. So what is a buffer? A buffer is a solution that will resist changes in pH, right? And we know that pH is the concentration of the hydronium ion or the negative log of the concentration of the hydronium ion, but it really tells us how much hydronium ion is in solution. And so you could imagine if you add a significant amount of a strong acid like hydrochloric acid or nitric acid, that the concentration of hydronium ions should drastically increase because we know that the concentration of the hydronium ion exactly equals the concentration of the acid. But what buffers do is they have this ability to resist that change in pH. And so we don't see the pH drastically decrease. If we add a strong base, our solution's pH doesn't drastically increase. So what buffers do is they neutralize added acids and bases. And so they have to have components within them where a component in the buffer neutralizes an acid. But then the buffer will also have another component that would neutralize the addition of a base. So they have to have two different components that are able to incorporate these different types of changes to pH. We see a lot of buffers prepared in laboratory settings. You're going to get to do to a lab using titrations you making buffers this week or next week, depending on which lab you're in. Buffers are commonly used in commercial products because we don't want resistant changes in pH. And then we also encounter buffers naturally in biological systems, or your book even focuses on what's going on in the ocean. And buffers are really important environmentally and naturally in our body. We don't want changes in pH. I want to be able to drink a glass of orange juice that has citric acid in it without it severely upsetting the pH of my body, and it gets too acidic. So we have buffers that are in our blood. We have buffers in our stomach. We have lots of different buffers that help keep us from having drastic pH changes that could be catastrophic for our bodies. And the same thing as the environment will do that too. So buffers, like I said, they need to neutralize added acids, they need to neutralize added bases. And how do they do that? What are their components made up of? Well, there's two different types of buffers. A buffer either contains a significant amount of a weak acid and its conjugate base, or a buffer is made up of a weak base and its conjugate acid. And why is this? We know that strong acids and strong bases completely dissociate to the hydronium ion or the hydroxide ion, and their conjugates are very weak, are so weak that they have no effect on pH. So the only effect on pH is either the strong base or the strong acid. And so there's only one component of strong acids and strong bases that's affecting the pH. But if we have weak acids and their conjugate base, the weak acid has partially ionizes into the hydronium ion, and that could counter and neutralize added base. And the conjugate base, on the other hand, of a weak acid can neutralize an acid. And I'm going to show different examples of it. But the key part of this is that for a buffer, it has to be a weak acid in its conjugate base, and it has to be a weak base in its conjugate acid. So go back to your chapter 15, refresh yourself with weak acids and their conjugate bases, refresh yourself with your weak bases and their conjugate acids. It's not going away. We still need this information. Well, how do buffers work? They work by what's called the common ion effect, which is based off of Le Chatelier's principle. Le Chatelier's principle, going back to chapter, what was that, 13 or 14, when we talked about equilibrium. Le Chatelier's principle says that when a stress is added to a system that's in equilibrium, the equilibrium will shift to reduce that stress. So weak acids and their conjugate bases, for example, when we look here at acetic acid reacting with water to form the acetate ion and the hydronium ion. So this is just our typical acid dissociation in water to produce its conjugate base and the hydronium ion. This is not a new reaction. We're still dealing with the same reactions as we had before. But in this case, if we have some amount of acetic acid and we have some amount of the acetate ion, we've made a buffer. So if our solution contains both of those components, then you have a buffer. And we have to have both of those components in significant concentrations, because if we add an acid, what's going to happen? If I add an acid to this reaction as it already stands, so this reaction's in equilibrium, I have amounts of acetic acid, I have amounts of the acetate ion, I add a new acid, and I can add something like HCl or HNO3. It does not have to be part of this reaction. I can add a totally different reaction. Well, what's going to be happening? If I add a strong acid like HCl or HNO3, we know that the concentration of that strong acid exactly equals the concentration of the hydronium ion. And so that's just like adding more hydronium ion to the reaction. And we already have that in our equation. So Le Chatelier's principle says if you add something that's already part of the equation, what are you going to do? You're going to shift away from that added product. And so we'll shift to the left. And so that's how Le Chatelier's buffers help resist pH changes when we have the addition of acids, if it's an acid dissociation reaction. If we add a base, however, in this case, we add a base, what's the base going to do? Well, the base, if we add sodium hydroxide, for example, what is the base? The base is exactly equal to the concentration of the hydroxide ion. And so that's like adding just hydroxide ion. And what is hydroxide ion going to do? Well, in fact, the hydroxide ion is going to react with this hydronium ion, H3O+, to make water. That's a neutralization reaction. So it actually consumes, it pulls out some of that H3O+. And so when we add a base, the reaction shifts to the right because the base will remove some of this H3O+. Okay? This is just the common ion effect. I'm going to point out that when we make buffers, you have to make buffers using both of the components of your weak acid and its conjugate base, or the weak base and its conjugate acid. As I'm going to point out here, we have acetic acid being added or made using just acetic acid because that's commercially available. But the acetate ion is not commercially available. You can't just buy that from a chemical supplier. So how we buy it is we buy it as a salt. Okay, so we buy it as, in this case, it'd be sodium acetate. And why isn't sodium in the equation? Because it's a spectator ion. And why is sodium a spectator ion? Because it's an alkali metal. And why is it an alkali metal a spectator ion? Because Na plus would be the conjugate acid of NaOH. And NaOH is a strong base, and strong bases completely dissociate. And so that conjugate acid does not have any effect on pH, so it's just watching the buffer do its thing. When buffers resist this change, we call it buffering action or buffer action. So this is a more descriptive representation of what's happening in a buffer. And so in this case, we have a buffer that's actually made of hydrofluoric acid and the fluoride ion. And we say that they're in equal concentrations. So I already have this buffer made of HF and F minus, and you can see that represented in this middle depiction, this middle figure, where we have the same amount of fluoride ions as we do HF ions, or HF molecules, excuse me. When you add OH, what ends up happening in this case, when you add a small amount of OH, it'd be reacting with the HF Again, our HF is going to react. It's going to make the water ion. So this is the same case. So showing exactly what we did with Le Chatelier's principle before. When we add OH, it shifts to the left and makes more water over here and the fluoride ion. This is a slightly different derivation of the reaction. When we add acid, on the other hand, you can think of acid as H plus or H3O+. They're synonymous with each other because we know H plus immediately reacts with water to form H3O. But in this case, if we just think about it as H plus, adding H plus would be the same thing as adding an acid. H plus is going to react with that F minus very strongly, a really strong electrostatic interaction, and it's just going to form more HF. So you can see here in our buffering action that yes, the HF concentration does grow a little bit. And on this case, yes, the F minus concentration does grow a little bit because it went in that direction, but they're not much. And in fact, the HF concentration when we added the OH decreased by the same amount that the F minus increased. And so if we think about the average, they're still in the same average as the buffer was here in the solution. Same thing happens in this depiction, where the F minus decreases by the same amount as the HF increases. And so their average is the same as at their original buffer. And so that's not always the case where it's going to stay exactly the same as what the buffer was before, but it's going to resist these large changes. So it's going to try to counter, like I like to think about buffers as countering or a balance, where you want to try to stay as balanced as possible. We can do a lot of calculations with pH, calculating the pH of a buffer solution. So we know that pH is the negative log of the concentration of the hydronium. So this hydronium ion, very, very, very important. And what can we do? Well, we can do exactly what we did in chapter 15, where if we know the Ka of our reaction, we know the initial concentrations of our weak acid and our conjugate base, well, then we can calculate equilibrium concentration of hydronium ion using an ice table. Woohoo, ice tables aren't gone. Okay, but there's a lot simpler way to do this. We don't have to do this all the time because the Kas of weak acids are small. We've got really small Kas. And so remember, when Kas were small, what did we do? We tried the X's small approximation. So if we have a small Ka, we can try the X's small approximation using what's called the Henderson-Hasselbalch equation. And I'm going to show how the Henderson-Hasselbalch equation was derived. But the Henderson-Hasselbalch equation, you have to be careful with this. You need to make sure, again, it's a proper buffer, a weak acid, it's conjugate base, they're in similar amounts. And it really comes down to that the concentration of your weak acid and the concentration of your base, your conjugate base, those initial concentrations, we don't need to get to equilibrium concentrations, okay, because we're saying the X's small approximation is valid and their concentrations are not going to change very much when they get to equilibrium. Makes sense again, right? Because buffers are trying to resist changes, so their concentrations aren't going to be changing. So if the concentrations of the initial weak acid and the initial concentration of the conjugate base are relatively large and the Ka is small, let's try the X's small approximation. Let's do the Henderson-Hasselbalch equation because it's this really awesome, simple calculation where you don't have to do an ice table. So what does the Henderson-Hasselbalch equation look like? Well, first, let's go back to chapter 15, our equilibrium reactions. Let's just take the generic expression for a weak acid dissociation with water. So we've got HA reacting with water in equilibrium with A minus and H3O+, where HA is our weak acid, A minus is its conjugate base. So the Ka expression is the concentration of my products divided by the concentration of my reactants. And this is supposed to be at equilibrium, but we're saying the X's small approximation is valid and we can use initial equilibriums. So if we start with that, but we want to get pH, right? The important thing is getting pH. So what do I really need? I need the concentration of the hydronium ion. And in a buffer, we don't know that right away, but we can figure it out. So what I want to do is I want to isolate the hydronium ion all by itself so we can eventually get to the pH equation. Okay? If I rearrange this slightly, I just pull out the H3O+, then I have that Ka equals the concentration of H3O+ times the ratio of the conjugate base divided by the weak acid, right? Now I see concentration of H3O+ times this nice ratio of the buffer pair. And that's great, but what's the problem with KAs? KAs are these really big numbers with powers of 10, right? Or they're really small numbers of power of 10, like 1 times 10 to the negative 15, or 9.7 times 10 to the negative 7. And those aren't really fun numbers to work with, but what are? Well, if I do my if I do the log, I do the negative log of things, what do I get? So if I take the negative log of this whole equation and do some little bit, we know our log functions, what this turns into is the negative log of the Ka equals the negative log of H3O plus minus, or plus, the negative log of A minus over HA. And so what is this? This looks a little bit daunting, but it's not really, because what is the negative log of the Ka? It's the pKa. And what's the negative log of H3O plus? It's pH. Okay, so now we have things in the P scale. Hey, we can't do the P of the concentration over the concentration. It's just the negative log of the relative concentrations for the weak acid and the conjugate base. But this is really nice that we've simplified our equation. We now have something in pH. We have some things in pKa. We know how to calculate these values. So what I get is I get that the pKa equals the pH minus the log of the conjugate base over the weak acid. And this becomes the Henderson-Hasselbalch equation. We just rearrange it just a little bit because we know pKa values. pKa values come from Ka values, and those are constants. Those are known values. They don't change. But pH changes. We don't know pH. We have to calculate pH. We rearrange this equation just a little bit to solve for pH instead of pKa. Then the Henderson-Hasselbalch equation is the pH of a buffer equals the pKa plus log of the conjugate base over the weak acid, where now I've written it out instead of HA and A minus, because it's always conjugate over the weak acid, or conjugate acid over the weak base. And this equation is wonderful. It's incredibly helpful for calculating the pH of buffers. So again, this works if we have a buffer that is in significant amounts of weak acid and its conjugate base. Ka is small. So this works. This cross-matching works, and you don't have to do an ICE table. If your Ka is big, your amounts of your buffer components are not relatively large, then you're going to have to do an ICE table. But all of the scenarios we're going to talk about, we're going to only do the Henderson-Hasselbalch equation. Okay, so how can you calculate the pH of a buffer? You can either do an ICE table, or you can do the Henderson-Hasselbalch equation. This is great for pHs. You may be asking yourself or thinking, wait, Dr. Coates, not all reactions are weak acids and their conjugate base. You told me a buffer could be a weak base and its conjugate acid. So what do we do with that? Because then we're going to have KBs and we're going to have pKbs, and it's going to take a lot of extra effort to get to the pH. And that's true, but there's another version of the Henderson-Hasselbalch equation. Okay? And so we can use the Henderson-Hasselbalch equation, another version of it, to calculate the pOH. And then you know that it's very simple to get from pOH to pH, because pH plus pOH equals 14. So super easy. So in this case, if we have a generic equation for a base reacting with water, we have B, we got its lone pair, reacting with water in equilibrium with the conjugate acid, Hb plus, to form OH minus. I'm not going to go through the same derivation again, but in this case, it's not pH equals pKa, it's pOH equals pKb plus the log of the conjugate acid over the weak base. So it's always the conjugate over the weak component, right? So this is insanely helpful so that you don't have to rearrange equations, convert KBs to KAs, and do the equation. Just do this version of the Henderson-Hasselbalch equation where you calculate pOH using this, where you know the pKb, or you can calculate the pKb using the negative log of the Kb. And then you have the concentrations of your conjugate acid divided by the concentration of your weak base. Take the log of that, bang, boom, you've got the pOH. Very simple to use equations. They have the same assumptions. Kb's got to be small. The concentrations of the weak base and its conjugate acid initial concentrations have to be relatively large. Okay? And I'm going to talk about what relatively large means in a little bit. So those are the Henderson-Hasselbalch equations. And we're not going to calculate, do examples of calculating the Henderson-Hasselbalch equation now, but it should be pretty easy calculations for you as you know how to do log functions. You're very familiar with that. It's my biggest hint is to keeping track of everything. Use parentheses, they're your best friend. Okay? But this should be a calculation that you don't need much practice. But I want to take this equation because we can use the Henderson-Hasselbalch equation, or really take this equation. We can use this equation to help tell us more about buffers and how buffers work. So we know we have these two versions, pH equals pKa plus the log of conjugate base over the weak acid, or POH equals pKb plus log conjugate acid over weak base. So when we have these equations and we have the Henderson-Hasselbalch equation, we can talk about the effectiveness of buffers. And the effectiveness of buffers, right? We want an effective buffer. We want a buffer that's going to resist changes to pH. Specifically, I want to resist changes. I don't want to just add 1 milliliter of NaOH to my buffer, and that's too much. It's too much. The buffer can't handle it. I want to be able to drink, like in the example of the orange juice, I want to be able to drink a whole glass, or in fact, like a whole gallon of orange juice and not have too much. You will definitely have some bad problems with heartburn if you drink a whole gallon of orange juice. I've had that. Listen to me. But anyway, I want to be able to have a significant addition of an acid or a base, and my buffer be able to handle that and resist changes to pH. But buffers have ranges, right? You can only add so much acid, or you can only add so much base before you exceed the effectiveness of the buffer and it fails. But that's okay. That's okay that the buffer is going to fail at some point. You just don't want it to fail after a very small addition of an acid or a base. So the buffer effectiveness depends on two factors. And the first factor is it's the relative amounts of that conjugate pair. We want that conjugate pair, the ratio, because if you think back to our equation here, the Henderson-Hasselbalch, we want this ratio of conjugate base to weak acid, or conjugate acid to weak base. We want that ratio to be as close to 1 as possible. Okay? Meaning the concentration of the weak acid, concentration of the weak base, we want that ratio as close to 1 as possible. The closer it is to 1, the more effective the buffer is going to be. The bigger we get away from 1, the less effective the buffer is going to be. So if that ratio is way too high or way too low, then it's going to affect that equation, and the pH effectiveness is going to decrease. The other factor that affects buffer effectiveness is the absolute concentrations of the acids and bases, meaning we want high concentrations. We don't want low concentrations. We want 0.1 molar. We want 1 molar. We want 10 molar, right? We don't want 0.001 molar of our concentration of our weak acid, or 0.001 molar of our conjugate base. Right? We want to have significant absolute concentrations. So it's the concentrations, we want them to be high, because the higher they are, the more they're going to be able to resist the volume of changes. And then the closer they are to each other, it comes into the Henderson-Hasselbalch equation. We don't want that log function to all of a sudden get really large or really small. So we take those two things into consideration, then we can work on what's called the buffering range. And the buffering range is the pH range at which a buffer is effective. I think that's really what it is. And so it's maybe a pH of 6 to a pH of 8, right? Or a pH of 7.5 to 9.5, but we've got this like window at which a buffer is effective, and then we consider that to be an effective buffering range, and then outside of that window, all of a sudden, pHs are going to change exponentially. They're not going to have small changes. Like I said, they're trying to resist changes to pH. It doesn't mean that the pH won't change a little bit because we're skewing that concentration, but the pH will change a little bit, but an effective buffer resists large changes in pH. So what is the buffering range? Well, a buffer is most effective when that concentration, because remember, that was the number one point in an effective buffer, when that concentration, that relative concentration, is close to 1, but really it's effective if it's greater than 0.1 and less than 10. So that's the effective buffering range for that point number 1 of the relative concentrations of our conjugate pair. And so that means if you actually go back and calculate the Henderson-Hasselbalch equation, so if we went back and we plugged in 0.1 over here, if you get the log of 0.1, what do you get? Okay, the log of 0.1 will get a -1. If you go to the Henderson-Hasselbalch equation and you take the pH equals the pKa plus the log of 10, if you calculate the log of 10, the log of 10 is 1. So the log of 0.1 is -1, the log of 10 is +1. So that means that the effective buffering range, the pH range of an effective buffer, is equal to its pKa plus or minus 1, right? Because it's pKa minus 1, the pH equals the pKa minus 1, or pH equals pKa plus 1. So if you want a buffer, for example, if you want a buffer that's going to be able to have a pH around 9, you want to pick a pKa that's close to 9. So you want its pKa to be about 8, because that's plus or minus 1. You want it right at 9, or it could be 10, because 10 minus 1 is 9. So you want it to be as close to your desired pH as possible. So the effective buffering range is a pH equal to the pKa plus or minus 1. So knowing the pKa of your buffers, which is really knowing the pKa of your weak acids, becomes important. This is exactly the same true if we have a weak base and its conjugate acid. A weak base and its conjugate acid, the effective buffer range for that is the pOH, is the pKb plus or minus 1. So it's the exact same scenario that it would be pKb plus or minus 1 if it's a weak base in its conjugate acid. So that's the effective buffering range, again, pKa plus or minus 1, or the ratio is greater than 0.1, but less than 10. So the buffering capacity is a measure of the ability of a buffer to resist large changes in pH, right? That's what we want. We want to resist these large changes in pH when we add a strong acid or we add a strong base, because we know adding a strong acid is just adding pure hydronium ion, and adding a strong base is just adding hydroxide ion. And so something that has a high buffering capacity, so the pH ranges is always the same. The pH range is always plus or minus 1 of the pKa or plus or minus 1 of the pKb, always the same. But the buffering capacity is that I can add more and more and more strong acid, or more and more or more a strong base, and my buffer will do a really good job of resisting significant changes in pH, right? It's still going to waver between plus or minus 1 of that pKa, and that's the buffering range. That's when it's a buffer, acting as a buffer. And the more and more base I add, or the more and more acid I add, and the pH continues to just barely change or resist changes in pH because the buffer is effective, and that's a good buffering capacity, or a high buffering capacity. A low buffering capacity would mean, my example before, you had 1.1 milliliter of NaOH and boom, your pH just shot up to the basic, like a pH of 14. Or you add 0.1 milliliter of HCl and boom, your buffer wasn't able to resist the change. And so it has a low buffering capacity and the pH goes down to 1. Right? So for a good buffering capacity, to buffer against a base, you need high weak acid concentrations. To buffer against an acid, you need high conjugate base concentrations. But really, it comes back to, you want high concentrations of both. They don't have to be exactly equal to 1. They just have to be between 0.1 and 10 for their ratio, but you want them as high as possible. You want those concentrations as high as possible. At 1 molar, 2 molar, 3 molar, that's great, but 0.1 is pretty good too. Okay, so you want them as good as possible. And we'll do some calculations to see, was our buffer effective or not, or did we exceed the buffering capacity really quickly? Okay, so to buffer against both an acid and a base, you really want them to have similar or even equivalent concentrations of the weak acid and the conjugate base. And remember here, every time I would say weak acid and conjugate base, I could very well be saying weak base and conjugate acid, because a buffer could be made of both. I'm just trying not to be as super redundant. Okay. So let's practice. And why not practice? So we have a potential buffer. We've got a few different scenarios where I'm making a potential buffer. So in this case, I have 0.1 molar of KNO3, potassium nitrate, and 0.1 molar of HNO3, nitric acid. And do you think this would make a good buffer or not? Well, let's break it down. First thing, do we have a conjugate pair? Well, remember, what is that potassium ion? It's a spectator ion. It's not doing anything. So really, I just have the NO3 minus ion and HNO3. And that's a conjugate pair. But what's wrong with this conjugate pair? HNO3. What is this? It's one of our strong acids. So this is not a good buffer because HNO3 is a strong acid, even though it's a conjugate pair, because that NO3 minus is the conjugate base of HNO3. Strong acids are not good buffers because what does that strong acid do? It completely dissociates into the H3O plus, and so your pH is really low and was not going to do good resisting changes to pH. Think of another scenario. All right, we've got 0.1 molar NaNO2 and 0.1 molar HNO2. And so in this case, I should have mentioned before, our concentrations are equal to each other. And so that's good, right? We want the relative concentrations to be equal, as close to 1 as possible. So the ratio, so 0.1 divided by 0.1 is 1. So that's good. And they're relatively high concentrations. 0.1 is a high concentration. So far, it could be a good buffer. Our next question is, do we have a conjugate pair? And does that conjugate pair come from a weak acid or a weak base in its conjugate? We look at this, and I see I've got sodium nitrite and nitrous acid. So sodium nitrite, we got NaNO2. That Na, what is it? Spectator ion. Not going to have any effect on pH, but the NO2 minus ion is the conjugate base of HNO2. And is HNO2 one of our strong acids? Nope, it's a weak acid. So this is a great conjugate pair, and could make a good buffer. We've got our high concentrations, and we've got a weak acid and its conjugate base. That's awesome. All right, our next scenario, we've got 0.1 molar HClO and 0.1 molar NH3. They're equal concentrations. HClO is a weak acid. NH3 is a weak base, but what's the problem with this one? They're not a conjugate pair, right? NH3 is not the conjugate base of HClO. NH3 is the conjugate base of NH4+, or the conjugate base of HClO is ClO minus. Okay? So not a good conjugate pair. Will not make a buffer. So as I just said, in this case, I kind of gave it away. We've got NH4Cl at 0.1 molar and 0.1 molar NH3. Is this going to be a good buffer? Well, NH4Cl is really NH4 plus and Cl minus. So we've got the ammonium ion and the chloride ion, and that chloride ion is spectator ion, right? It's the conjugate base of HCl, no effect on pH, right? And then NH3. So great buffer. This is a good example of a good buffer because we have the ammonium ion, which is a weak acid, and NH3 is a conjugate base. Or you could think of NH3 as the weak base and NH4 plus as its conjugate acid. Think about it either way. Our last scenario is using 0.001 molar NaHCO3. So that's sodium bicarbonate and carbonic acid H2CO3 in 0.2 molar. Okay? And hopefully you're just like, red flag, red flag, red flag. There's a lot of things that are wrong with this. Okay? Specifically, the concentrations are not close to each other. So 0.01 relative to 0.2 is not in between 0.1 and 10. It's not close to 1 at all for that relative concentrations. So that's the biggest problem. Specifically, the 0.2 molar is great. That's high concentration, but the 0.001 molar is way too low of a concentration. So these defeat the effective buffer factors. Too low of a concentration for that sodium bicarbonate, and the ratio between my weak acid and its conjugate base are not close to 1. They're not between 0.1 and 10. Okay? But if I didn't know the concentrations, or if they were equimolar and they weren't defeating those purposes of the Henderson-Hasselbalch equation, is NaHCO3 the conjugate base of H2CO3? It absolutely is. That HCO3 minus is the conjugate base of H2CO3. But it could be a buffer if we fixed those concentrations. It's not a buffer because, yes, that is Yes, it is the weak base, and H2CO3 is the conjugate acid, but the concentrations are okay. So the concentrations are correct. All right. So can you identify a buffer? Can you apply the Henderson-Hasselbalch equation? If you can, you're going to do great for the beginning of this chapter 16, right? The next thing that you can do to buffer is you can stress it out, right? So the Henderson-Hasselbalch equation allows you to calculate the pH of a buffer. I just talked about effective buffering range and buffering capacity. So what happens when we stress out the buffer? Well, Chatelier's principle says that the equilibrium is going to shift, and we're going to see that shift by going one direction or the other direction, and so thus the pH must change, okay? Because you're either consuming H3O plus or you're making more H3O plus, you're making more of your weak acid, so the pH has to change somehow. And so what we can do is that when we stress out that buffer, when we add some acid or we add some base, we can actually calculate the pH of a buffer. And we're going to do this using two components. And the first one is you got to know the stoichiometry, right? So you got to know the stoichiometry. When you have an addition of some chemical, it's going to increase the concentration of another component, thus decreasing the concentration, right? If we add acid, it's going to decrease the concentration of the conjugate base, but it's going to make more weak acid. If I add a base, it's going to decrease the concentration of HA, and so it's going to make more of the conjugate acid. So what does this sound like? This turns into a limiting reactant problem. So that's why it's stoichiometry, because it really turns into a limiting reactant problem. We're going back to semester 1 of Gen Chem. It's going to be a blast. We're going to do limiting reactant problems, but it's simpler than the stoichiometry we did before because we're going to have tables similar to ICE tables, but not the same tables. I'm going to call them limiting reactant tables, okay, that actually help us keep track of what's the limiting reactant, how are things changing from where we start, where it changes, and what's our final concentration going to be. Then we can do the Henderson-Hasselbalch equation. Okay? So yes, we don't have to do ICE tables all the time, but we're going to bring back in some helpful stoichiometry or limiting reactant tables to help us with what happens when we add acids and bases to stress out buffers. How do we calculate the pH? Okay? Because then once we know that, once we go through our table, our pseudo ICE table or limiting reactant table, we'll be able to get to the new equilibrium calculation concentration of H3O plus. So now we will know the pH, new pH, not just the pH of our buffer, but the new pH of our solution when you add acids and you add bases. Okay. So this is all going to be a ton of fun that we're going to do in the next lecture. So bring your calculators, get ready to draw some ICE tables and limiting reactant tables, and calculate the pH of buffer solutions. All right. Good luck. I hope that this was very helpful, and I enjoy the reading and enjoy the, can get started on your homework, and don't forget to do the quiz. All right, bye.